Hi students. So we'll study today one more topic, that is radiation. So in the transfer of heat I already discussed part 1 and part 2 about the conduction and convection, and part 3 is for the radiation. So if you did not watch the part 1 and part 2, please go and watch it, and part 3 so for radiation no we'll discuss detailedly, right? So what is meant by the radiation? Like we are receiving the radiation from where? From the sun. No? Sunlight is nothing but radiation. You know that every object will radiate. Even our human body is also radiate the certain amount of radiation. So we are losing the energy in the form of a radiation now, right? Even this bulb is the building, or even at 0 degree centigrade ice also will emit certain amount of radiation now, right? Which object will not emit the radiation now? If an object is maintained at absolute zero, like minus 273 degrees centigrade, so therefore it is not going to emit any radiation now. So apart from that, so every object it will be able to emit the radiation now, right? So therefore amount of radiation based on the temperature on this, and will related to that loss theories also will study now, right? So this radiation so does not require any medium. So what happen now? This radiation do not require any medium for its propagation. So therefore it is nothing but a electromagnetic wave. So that are called like warm waves, that is nothing but a infrared radiation. Clear? We know that therefore it will be the speed of the, will travel with the speed of the light 3 into 10 the power of 8 meters per second now. So this is the fastest mode of the transfer of heat, and it does not require any medium. See, if we are standing in a sunlight now, we will receive the energy from the sun now, right? So now now we'll see if upon to that any body no, therefore if it is a radiation is falling, suppose some amount of radiation is falling on our body, what will happen now? Our body will observe certain amount of radiation now, and some bodies will transmit the radiation, some bodies will reflect the radiation now. So therefore here suppose any one body is there, no, this is one body. So upon to this body there is a certain amount of radiation which is entered, I mean incident onto this one. Radiant energy, suppose I am assuming that it is E. Therefore this radiant energy, some amount of energy is absorbed, so therefore it will be absorbing, and some amount of radiation is reflected, some amount of radiation is transmitted, some amount of energy is absorbed now. Therefore amount of absorption, what is the absorptivity now? Absorptivity is nothing but a amount of radiation which is absorbed by amount of it is incident onto this. Similarly, so reflectance, so we can write down amount of radiation which is reflected, so by amount of radiation incident onto this. So transmittance no, therefore amount of radiation which is transmitted are by amount of radiation incident onto this. If you add of all this one now, so absorptance plus reflectance plus transmittance, so you can add it EA plus ER plus ET. So this is nothing but a total amount of energy incident no, so it will be always equal to 1 now. Clear? So if any object you know, if it is observing more, so therefore so that object is said to be like a good observer. So when it is observing more, so what will happen now? Therefore its body it is going to get increase its temperature. See, observing the radiation means gaining the energy. Gaining the energy, how it will store? It will store in the form of a temperature, I mean vibrational kinetic energy. Temperature of the body will increase. If any object is there, it is observing very good amount of, so lot of absorption is there, no, definitely temperature will increase. So when temperature is increases, it is going to emit the radiation onto this sun. Therefore a good observers are good emitters. This was given by Kirchhoff law. Kirchhoff law of radiation no. So what is this law? Kirchhoff so law of radiation no, any object, therefore a good observers are good emitters, right? So in mathematically we can say that, so emissivity or emissive power of the, so any body, so any one body by its absorptive power of this body. So amount of emission by absorption. So good emitters are good observers, no. Therefore this ratio of any object, no, it will be equal onto this. So for one object it will be equal. So finally it should be equal to one thing, no, that is nothing but a so emissive power of our black body, no. Therefore emissive power at particular wavelength of a black body. So what is this black body? No, we'll study. No, so this mathematically or right we can define. So Kirchhoff law of radiation. So one more thing is also is there, like a previous theory of heat exchanges. What is this one now? Simple thing. Suppose we are staying in the some surroundings now. So surrounding temperature is about. So we can explain like this. So here suppose here we are staying. This is one surroundings now. Suppose in the room is there. You are in the room. So this is one person. So temperature of this person is about 36 degrees centigrade now. So outside temperature is about surrounding temperature is how much now? 27 degrees centigrade. Suppose he is staying in the AC room, right? So what will happen now? Therefore, which one is cool now? So surrounding temperature is cool. So definitely it is going to lose the certain amount of radiation. So when you are losing the radiation, no, we feel it as cool. So whenever you are suppose if any one person is there, suppose this person is staying in one room, hot room. Let us assume that his temperature is 36 degrees centigrade. Temperature of the surroundings is 40 degrees centigrade. So what will happen now? See, a surrounding temperature is greater, no? So greater. So therefore, what will happen now? Heat will flow from surrounding temperature to this body temperature. So we are receiving the energy. When you are receiving the radiation, no? So we feel it as warm. When you are losing the energy, we feel it as cold. Okay. If it is at equilibrium temperature, that means so one person is there. So at equilibrium temperature, that means so temperature of the surroundings and temperature of the this is one person is there. So temperature of this person is 36 degrees centigrade and surrounding temperature is also 36 degrees centigrade. At this point, therefore, some amount of energy will be radiated, no? See here. So he will give some amount of radiation, no? So that much amount of radiation it will be able to gain it. So how much we lose it, that much we gain it, no? So that we cannot raise the temperature, we cannot decrease the temperature. So this exchange we will call it as like a Prevost's theory of heat exchanges. Theory of heat exchanges. Right? In this way, you can understand that. So therefore, when we feel it as warm in the summer season, why we feel it is warm? Because of due to we are gaining the radiation from the surroundings. Clear? So here we need to study about the black body. So why black body now? See, any other for comparison, like if you are comparing the density of the water, density of any substance, we will compare with the density of the water. Like if you are calculating relative density, the refractive index. So therefore you will compare the speed of the light in a different medium with respect to the speed of the light in vacuum. Like that. So for a radiation, no, we need to have one ideal thing, no. That ideal one we can take it as like a black body. So what is this black body now? Black body does not mean that it should be like a black color. No. Therefore, a black body is said to be like a 100% absorber now. Therefore, if any radiation is falling, so that all the radiation should be absorbed by that substance now. Alright? So that type of body is said to be like a black body. Like a black hole is there, no? Even light it will falls, definitely it is going to absorb. Therefore, black hole is assumed to be like a 100% absorption will be there. So a black body, what you can say, no? You can say that it should be have 100% absorption. Right? So if it is observing, a good observer is there, a good emitter, no? So therefore it is 100% emitter should be there. So it should have 100% emitter. So when the body will emit the 100% emission now, so when that body temperature is very high, so therefore it is going to emit the radiation. Almost all possible radiations, no, it will be emitted. So 100% emitter is nothing but one stars. So stars are considered to be like a black bodies. Like so 100% absorption is nothing but a black hole. Right? So black hole. So like this we can consider like a black body onto this. Therefore, here 100% absorption or 100% emission, or absorptivity of this one it will be equal to 1, or emissivity will be also equal to 1. Therefore, that type of body is said to be like a black body. Even in our laboratory, therefore, we designed like one black body, therefore that is sphere is black body, So here there is one ball, it is made up of this ball. So therefore here outside there is no need of any color onto this one, So but here inside this one, there is a lamp black is done now. Lamp black coating is done now. So suppose any radiation, okay, small hole it is there, any radiation which is entering into this one, So here at the edge of this, therefore there is a one sharp edge, it will be present here now. If any radiation is coming and falling on this one, So what will happen now? Therefore it will undergo like a reflection onto this. So like this it will be able to undergo like a multiple reflections now. Whatever the light which is entered, so it will be able to reflect back inside this one only, and it will never return back onto this one. So this is said to be like one practically a perfect observer, like we can treat it as like a black body. So therefore by using this black body concept, so we have two theories related to the radiation. What is this one now? For black body radiation, so therefore Stephens-Boltzman law. Stephens-Boltzman law. What is this Stephens-Boltzman law? So therefore this Stephens-Boltzmann law, therefore for this they told that for the black body, see black body is there now, see here like a star is there, like a sun is there. So what is the surrounding temperature of the sun? See, we are living in some surroundings onto this sun. The surrounding temperature was created by the sun. So surrounding temperature now. So their star is there. Star is having higher temperature onto this. He is only the creator of the surroundings. Therefore, there is no surroundings for the stars. No, they are, because they are only the creators. No, therefore, so here at that particular region, so a star is a particular, it is act like a black body onto this. There is no surrounding temperature for a black body. Therefore, if temperature is more, so therefore emission of radiation of energy is also more. So like there is a one star is there, this is one star like a sun. So star, therefore our sun, So sun surface temperature is T, so it is going to emit the radiation in all the directions, So amount of radiation emitted per unit area per unit time, this is nothing but like a intensity. Therefore amount of energy radiated per unit time per unit area. So R we can write down intensity. What is the formula here? Amount of energy emitted per unit area per unit time, R. So energy by time is nothing but power by area. So intensity, therefore intensity is directly proportional to amplitude square, right? So amplitude square, and intensity is also inversely proportional to the square of the distance. So keep in mind these values, these formulas, so that it will be useful for our calculations. Intensity is directly proportional to the amplitude square. Amplitude here we do not require onto this one. So therefore intensity is inversely proportional to the square of the distance. If we are going far away, intensity will decrease. So therefore Stephens-Boltzman law, what is this says now? Energy emitted per unit area per unit time at a given wavelength is directly proportional to fourth power of absolute temperature of the body. Therefore surface temperature of the body, we have to take it surface temperature. Absolute temperature should be absolute means what? So it should be measured in kelvins, right? So here we can rewrite it as, so energy emitted per unit area per unit time, you can write down sigma into T to the power of 4. Clear? So suppose they may ask you power. What is the power? Power is nothing but energy by time. So you can write down sigma into A into T to the power of 4, or energy, if they are asking energy, right? Energy emitted, therefore sigma into A into T to the power of 4 into T. These all are the formulas for this one. No? So this one. What is this sigma now? Sigma is nothing but Stephens constant. What is this Stephens constant? No? Let us see. Right? So here, therefore here sigma is nothing but Stephens constant. So this was given by Stephens constant, therefore 5.67 into 10 to the power of minus 8. What is the unit for this one now? Here Stephens constant taken here, no? power. This is power. Power is nothing but a watt by meter square Kelvin to the power of 4. Watt by meter square Kelvin to the power of 4. This is the SI unit now. We'll write down dimensional formula. What is the dimensional formula? Power. Power we can write down m1 L2 T minus 3 by, so this m square, that is nothing but L square into K power 4. So this will get cancelled. Therefore, here m1 L0 T minus 3 K minus 4. So this it will be the dimensional formula for Stephen's constant. And these all are the formulas is for black bodies only. Why? Therefore, their emissivity will be always equal to 1. So similarly, if you want to calculate for a normal body, like how much amount of radiation we are emitting, our body is emitting now, we want to calculate. So for normal body, see, so for black body, what we written now? For a black body, so what we got this value now? So energy emitted per unit area per unit time, it will be equal to sigma into T to the power of 4. This is for black body. Why? Emissivity will be equal to 1. But for a normal body, so here for a normal body, so our like a human body, therefore for our human body does not have that much high temperature onto this, so we cannot create the source onto this. Even the bulb at that particular small region, no, we can, it lack like a black body, no. So one tungsten filament is there, no, in that small region, because it is a creator there, no. So here normal body, so we will live under the surrounding temperature on this. So here surrounding temperatures also will plays very important role. So for normal bodies we can write down energy emitted per unit area per unit time, it should be taken as emissivity into sigma into T power 4. This is the body temperature minus T naught to the power of 4. Suppose our body temperature is greater than surrounding temperature, we will be losing now. Suppose we are gaining, so surrounding temperature is greater, our body temperature is low, we are gaining, means at that time just write the reverse of this. Clear? So therefore here emissivity of the black body is 1. For normal body we cannot emit 100% of this, so because temperature is very small, no, so therefore energy emitted per unit area per unit time, so for a normal body which is kept on the surrounding temperature is, this is the formula, right? So you can calculate, but 100% most important point is what? T should be compulsory in kelvins only. Kelvins only, very very important, not in degree centigrade onto this. Clear? So this is Stephen's law. Now we'll go for another one more law, that is Wien's displacement law. What is this Wien's displacement law? Very very important. So this law is having lot of practical applications, no. Let us see what are there, no. So Wien's displacement law. So therefore Wien's, he conducted one experiment on a tungsten filament, no, by changing its temperature onto this one, no. So what he did now, see here. Therefore here we'll draw the graph here, no. He drawn the graph. What is the graph here now? With respect to the wavelength. So energy, emissive power, this is an emissive power. So emissive power means what? Amount of energy emitted per unit area per unit time at a given wavelength. So therefore here amount of energy emitted per unit area per unit time at a given wavelength onto this, right? So very very important now. So therefore that is nothing but a intensity by wavelength. Therefore he took that tungsten filament and he started supplying the electrical energy, so started heating. So therefore at particular temperature, so he observed, so therefore what will be the maximum amount of energy emitted per unit area per unit time at a given wavelength now. So he drawn the graph now. How the graph he got it now? At a particular temperature he got the, so the graph was like this. Okay, so now the graph is like this now. So this is a particular temperature, no, temperature T1. So wavelength is lambda 1. What happened now? Therefore here, so again then he increased the temperature of this one now. He calculated only maximum wavelength, maximum energy only. energy emitted per unit area per unit time per maximum intensity. So similarly, he increased the temperature, then he observed like this, the graph was coming like this at temperature T2. So therefore maximum energy got at this wavelength lambda 2 no. So therefore here again he increased the wavelength, increased the temperature no, therefore again he got the radiation graph like this. So this is for lambda 3 at temperature T3. So therefore here as temperature is increasing, that means T3 is greater than T2 is greater than T1. So when temperature is increasing, so maximum amount of energy emitted that wavelength at that particular corresponding wavelength, so the wavelength was decreasing now. So not all the wavelengths, keep in mind, not all the wavelengths, only the maximum amount of energy. So at that corresponding wavelength, no, that wavelength only is decreasing now. This he observed that, so then he gave one law related to this one, no. Therefore, he said that, so for a black body, no, therefore here amount of therefore wavelength is inversely proportional to the absolute temperature now. This wavelength should be compulsory, it should be for maximum intensity only. Then if I remove this proportionality, I have to place one constant B by T. So what is B now? B is nothing but a Wein's constant. It is got it as 2.9 into 10 to the power of minus 3. So this for meter into Kelvin. So this was the B value. So lot of significance is there now, and it does not depend upon any other shape, size of an object, what is the material and all this, no. It does not depend. It depends upon only on the temperature onto this one. So therefore, by using this law, so we can calculate the temperature of any celestial body. So we know that surface temperature of the sun is nearly 6000 kelvins now. Who measured it now? How we measured that? Who went there stars, for the sun, and who measured this one now? How we came to know that the surface temperature of the sun is 6000 no? So that was one explanation. So one can be calculated by using this one now. From the sun, what is the maximum amount of intensity is coming out? So then by using that value, so they can calculate the temperature. Even in corona time, therefore we measured, right? So the body temperature by keeping like a thermometer gun. So without touching our body, we measured the temperature now. How we measured this one now? How that gun is measuring the body temperature now? See, suppose if you are getting fever, so what you will do? So therefore our body temperature will be higher. So when its temperature is higher, so our body emit the radiation with a lower wavelength. So that wavelength will be determined by that gun, no? So with that wavelength, it will determine the body temperature on this. Clear? So like this, so by using this one, no, we can determine in any celestial body, like in the space, lot of stars will be there. Upon to that star, which type of material is present, right? So by determining the wavelength, so by determining the temperature, so we can determine what type of material is present on that surface now. Clear? So and also this law tells that suppose if you are heating the any iron is there, if you are heating it, so what will happen now? Initially you will see that a red color. Therefore, if you are continuously heating, you will see that red color of the iron now. So then afterwards again if you are heating, it will come to yellow. Then again still you are heating now. Therefore, it comes to blue. Why? Therefore, as the temperature is increasing, so wavelength is decreasing. We know our visible spectrum, no, VIBGR. Wavelength of your red color is larger than wavelength of the blue color. That means wavelength of your yellow and blue color. So therefore, for temperature of the red is smaller, temperature of the yellow, therefore temperature of the blue. Therefore, to get the blue one, no, therefore you require very large temperature onto this one. No. Like that color of the heating body, no, so then also can be determined by using the Wein's displacement law. And we can also determine the surface temperature of the sun by using this law only. Yes, so that's why this is having lot of physical significance, no, lot of applications are there based on this law, no. So most important concept. So please go through it, no, go through thoroughly. So like based on the conduction, radiation, we'll do like a one numerical one video. So all the different type of different type of numericals, no, we will collect it and we will do a one video so that you can study very thoroughly onto this. So meanwhile, you please be thorough on this topic, no. So remaining things, no, we'll discuss in the problems part of this chapter, no. Thank you. Please subscribe to my channel.